Okay, so the plan today is to finish just a little bit of an example in section 2.3 and then cover 2.4. We're actually going to push 2.5 to next time. That'll basically just build off of some of the stuff we've done in 2.4. It's not I don't think a big leap in difficulty. Basically, we're going to take what we learned in 2.4 and then just add one more step at the beginning where we kind of get rid of fractions in the first step. So that's the plan for next time. I also posted a YouTube playlist. Let me actually bring that up here. Oops, wrong tab. I don't know if you all are like me, but I have like 1,000 tabs and windows open at any time. So navigating to my right tab, and then I'll show you where that's located. Okay, so under the useful websites tab on the Blackboard site, I've added this new line of text here. Well, there should be a space after this, but where it says the YouTube playlist can be found here, and here is a hyperlink. So you can click on the word here and it'll bring up my YouTube channel. And I posted our first 3 class meetings. So I'll be posting these as we go along on YouTube. I'll also keep posting them to the Zoom recordings tab too, just so that you have them in both places. I hadn't previously really posted the class meetings to YouTube, and mainly because it's just a little easier for me to copy the link over for Zoom and post the Zoom link. But I thought that it was a good thing to start doing for a couple reasons. One is that sometimes YouTube is just a little easier for folks to access. Maybe you can get to it on your phone a little easier, or pop it up on your TV while you're eating dinner or something if you wanted to review. And the other reason is that Zoom auto deletes the recordings after, I think it's 120 days. So if you were, say, moving on to your next class, Math 108 or something, and you wanted to come back and review some of the material that we covered, then you might want to go back and look at some of the lectures and so on. But even if you save those Zoom links, the recordings might be deleted by the time you say were to take 108 maybe in the fall or something. But this way, having them on YouTube is just a little bit more permanent that way, so you can come back and review those lectures. Is 2.5 still going to be due Sunday, or are we waiting? Yeah, I'll push 2.5 back. Let me actually write myself a quick note just to make sure that I remember to do that. I use my email as my note-taking app. There we go. Sent myself an email so that I won't forget it. Yeah, so we'll push the 2.5 homework to next week, and we'll get through 2.4 today. All right. Yeah, so definitely, I mean, linear equations are definitely a challenging topic. That's what we're going to be covering, in a little bit more depth today. We're going to do maybe an exercise that I hope will maybe just help a little bit, maybe give you a different strategy or a different approach that you might be able to use to kind of to work through the steps to work through a linear equation. Maybe just a little bit of a different, more descriptive way of looking at it. That's the word I was trying to look for. Instead of kind of an algorithmic way, maybe a more descriptive way, maybe something that could make a little bit more sense to you. So hopefully this exercise that we do today will help a little bit with that. But then of course, some of it is just getting used to the material, just drilling some of these problems. Sorry, I'm trying to do a couple of different things at the same time here, but some of it is just drilling the problems, getting a little bit more used to the material, getting a little bit of practice with the solving linear equations or solving different types of linear equations, recognizing, oh, okay, this is this type of one-step equation, or this is the first step I need to do. So some of it is just a little bit of that practice and drilling and pattern recognition. Some of it is, maybe I can give you a slightly different way to think of it today. And hopefully hopefully after today's lecture and after going through some of the homework in 2.4, things will start to gel or to click a little bit. But obviously we've spent a good bit of time already dealing with linear equations. So this isn't kind of a trivial little simple topic. We've spent several class periods already, and we've got another one or two to go talking about linear equations. So definitely a topic that is worthy of spending some time and effort to learn, and one that is really a foundational topic going into future courses as well. So it is actually important to master the topic. Okay, so let me get my other screen back up here. There we go. And kind of a little bit on that note, the quote of the day for today is from chess grandmaster Daniel Naroditsky. He does Twitch streaming and things. He's on YouTube. I like watching him. He's kind of fun to watch for like advanced beginner, early intermediate players. And one of his quotes or his ideas is that there's a difference between abstract and concrete advantages. So in chess, an abstract advantage might be something like I have a lead in development. Maybe I have 3 of my pieces out from behind my pawns and my opponent only has 1 piece out. And that's an advantage for me because I just have more options with more pieces out, more things I could do. But if I fall asleep at the switch for a couple moves, all of a sudden my opponent catches up. My opponent gets a couple of their pieces out and we're back neck and neck. That's as opposed to, say, a concrete advantage. If I have my 3 pieces out, my opponent has 1, and I can translate that into an attack and maybe win one of my opponent's pieces. If I win my opponent's, dark squared bishop, my opponent doesn't have a dark squared bishop essentially for the rest of the game. So that's a very concrete advantage. That advantage doesn't go away over the course of the game. So yeah, I can try to make it bigger. Let me zoom in a bit. That's about how far I can zoom in, but you can always, zoom in on your side as well. But hopefully that makes it a little better. Yeah, so the idea is that there are sometimes abstract advantages that give us the ability to turn them into concrete advantages. But if we don't actually do something to turn them into concrete advantages, that can they can never really materialize. So in academics, what does that idea look like? Say maybe getting a degree versus working in a career. You've always wanted to go into this certain career field, let's say nursing. Well, starting college to go into nursing and working through your coursework and all of that is great. That's a wonderful step in the right direction. Getting your degree is a huge achievement. But if your goal is to actually be a nurse and work in that field and help folks, having a nursing degree doesn't actually get you there. Having the degree is, or for any other degree for that matter, I'm not picking on nursing. It just first one that came to my mind. So having that degree is an abstract advantage. It gives you the ability to get into that career and do what you love and have a great career. But you have to do some extra stuff on top of that. You have to apply for the job. You have to do the networking. You have to maybe do the certification exams, all these kind of things that also play into that. So converting that abstract advantage, say a degree, into a concrete advantage, the career that you want to work in, does take that extra leap. And I would say the same thing with something like, like I was mentioning, solving linear equations. This is a challenging subject. It's something that's not gonna, you're not gonna watch me do it once and be perfect at it. So watching the lectures, that's kind of an abstract advantage. Taking notes and so on, that gives you a leg up. and you'll have a little bit better understanding. But, if you go 2 weeks or something and never touch the material, that's going to kind of fizzle away and you're just going to completely forget anything that we did in lecture. But if you go to WebAssign and you follow that workflow pointers document and you say, okay, we covered some stuff in 2.4 today, let me go right over to WebAssign this afternoon, work, 5 to 10 problems in section 2.4 on WebAssign. That helps to solidify that learning from today. And then you come back tomorrow and you finish up the 2.4 material and start pre-reading 2.5 for next week. That goes further into making that learning concrete, into making it stick, really solidifying that understanding. Just seeing a lot of different patterns in math is really a benefit. So math is a lot about pattern recognition, kind of like chess is. And just seeing a lot of these different patterns really helps you to say, oh, okay, here's this equation. Maybe today you don't have a really solid understanding of what the strategy is going to look like to solve this, but maybe a week from today you'll say, oh yeah, looking at this equation, I can probably guess what the next 3 or 4 steps are going to be to get the solution. Okay, so that is the introduction for today. And I wanted to do one more example from 2.3. Somebody asked a question about this, and I thought it was a good example to go over, especially because we're going to use this as a jumping off point for that exercise that I was talking about. So let's solve this equation. I suppose we really ought to say solve this equation. And remember what we mean by solve, just to remind ourselves. This will come up later on in the class today. So when we say solve, what I really mean is I want to find the value, find the number that I can replace into the variable w to make both sides be the same number. So when I simplify both sides, I get the same number. That's what I mean when I say solve, just as a reminder, because I think you'll see later in the class why I'm giving that reminder. I'll probably say it a couple other times throughout class today as well. So let's take a look at this. We have variable term, constant term, variable term, constant term. So we have variable and constant terms on both sides of the equation. And remember, the first thing that we want to do is we want to get back to an equation that looked something like our simplest, or one of our simplest one-step equations. So if I have, say, a number times w equals number, that's a one-step equation. I can solve that pretty easily, right? That's a pattern that by now I'm pretty familiar with. Or maybe if I had like w plus number equals number, that's also a one-step equation that I'm really familiar with how to solve. But we saw that usually we end up with the kind of number times w, or number times variable equals number situation. So what do I want to do? I want to get my variable terms on one side and my constant terms on the other side. So I'll start by getting my variable terms on one side, and I think I'll subtract 1.1 w off the right-hand side and off the left-hand side. Now I could do this in one step. I could also try to get the constant terms on the same side in the same step. And if you're comfortable with this material, you can definitely do that. We're going to take this one step at a time, and this is really going to lead into what we're going to do next. So make sure that you're writing down all of these steps that I'm doing in your notes as I go through them, because we're actually going to use this problem for another application or another piece of work in a little bit here. But 1.1w minus 1.1w is 0, and then I have plus 10. On the left-hand side, 2.6w minus 1.1w. What's 2.6 minus 1.1? 6 minus 1 is 5. The point comes down, and 1. So I get 1.5w minus 50 equals 10. Now I have my variable terms all on the left side, and I've combined them, I've simplified. I want to get my constant terms on the other side, so on the right side. So I need to get rid of this plus or this minus 50, and I'll do that by adding 50. So plus 50 to the left, plus 50 to the right. Minus 50 plus 50 is 0. I'm left with 1.5 W on the left equals 60 on the right. And now I have number times W equals number. I need to divide by the coefficient of my variable, 1.5. So I need to divide by 1.5 on both sides. And I get W equals 60 over 1.5. Now, as far as finding a solution, this is, this is a solution, but it's not in a very nice form. So let's look at how we could simplify this. And there are two approaches we could take. One approach we could take is the fractions approach. We could go this route because 1.5 fairly easily turns into a fraction. So I note that 1.5 equals 3 halves. So then 60 over 1.5 equals 60 divided by 3 halves. And I remember that if I have a fraction in the denominator, I invert and multiply, right? I flip the fraction over and I multiply against what's in the numerator, which would be 60, or I'll rewrite that as 60 over 1, just to make it clear that this is a fraction, the 60 is in the numerator, and I just have a 1 in the denominator. Now 60 times 2 is 120 over 3, and 120 over 3 is 40. The other approach I could take is a more direct decimal-based approach. 60 over 1.5. I could, instead of switching this into a fraction, maybe sometimes I have a decimal like 1.37 or something that's maybe a little messy to switch into a fraction. But I could ask myself, well, if I just want to get rid of the decimals, if I don't want to switch that 1.5 into a fraction, but I want to get rid of the decimal, what could I do? Well, I know if I multiply 1.5 by 10, that moves the decimal one place to the right, and I just get 15. So if I could multiply 1.5 by 10, I would just have a denominator of 15. That would be easier to work with. Of course, I need to multiply by 10 in the numerator as well, though. So what do I have? I have 60 times 10 in the numerator divided by 1.5 times 10 is 15. Now here I could multiply the numerator and get 600. But I think what I'll do first is look for my prime factors of 15. I know 15 breaks into 3 times 5. And I'm going to ask myself, I already have 2 factors in the numerator. I already have my numerator factored a little bit into kind of working towards its prime factors. So I don't want to really undo that by multiplying and then have to, factor everything out again. Is there a factor of 3 in, let's say, 10? Well, no, there's not, but in 60, there is. 60 is 20 times 3. Those 3's can divide out. So after one step, I'm left with 20 times 10 over 5. And then I can ask the question again, is there a factor of 5 in either of the two factors up top. There's a factor of 5 actually in both of them. 5 times 4 is 20, or 5 times 2 is 10. I'll cancel the 5 in the denominator with the factor of 5 and the 20 in the numerator, leaving me with a factor of 4 left over times 10 is 40. So if I have to simplify decimals, I can either go the route. Sometimes it works nicely to convert it to a fraction and then work in fractions. But I know that a lot of people really don't like fractions. If you want to try to avoid fractions, you could just try to handle it directly as a decimal. Now, kind of maybe a mathematical secret is that fractions really just are, or decimals really just are fractions, right? What did I do when I was thinking of making this change? Well, all that I really did, see that 10 over 15 there? I really just thought of 1.5 as 15 over 10, and then I inverted and multiplied, right? I just got 10/15 times 60 over 1. I really did kind of the same thing I did over here, except I used 10/15 instead of 2/3. So, I mean, how much different is it? Maybe we could debate over that, but I think the example on the right-hand side maybe feels a little less fractiony than the example on the left-hand side over here. So just a quick review for some fractions and decimals. But again, if you get to this point and WebAssign wants it in the simplest form, and as a fraction that's in lowest terms where there are no common factors between top and bottom, and where it's just integer over integer, we still have a little bit of work to do, and just being careful with these steps over here. That's as much a part of getting the correct answer at the end as knowing how to get your variable terms on one side, constant terms on the other side, things like that. Okay, so hopefully you've written down these steps over here. So let's jump over to our worksheet, and we're going to do a little exercise here. This is something that I do every once in a while when we kind of come up against a maybe like a multi-step type of problem. Yep, no problem. Yeah. If anybody ever needs to come in late or leave early, or pop out of the meeting, that's never a problem. You can always pop in and out. Yeah, that's not a problem at all. So when we have an application that has multiple steps, where it's a little bit complex, or we have to have our steps in the correct order, I've heard this sometimes referred to as something like Cornell notes. I'm not sure if that's technically the right word or application to use here, but this is kind of the idea. We worked through an example, and we worked through one in class, but you could also, if you were reading through your textbook, you could find a worked example and you could do the same kind of thing. We worked through an example where we worked it out step by step. So the first step that we're going to do is we're going to look at that example. We're going to, copy it down in our notes, write down each step by step, what we did in class or what's done in the textbook, whatever. We're going to copy it over. Then off to the right of those steps, we're going to describe each step in our own words. So what I would do if I was doing this in my notes, I might draw a line like this, and literally just a little bit off to the right on the same piece of paper, I'll write, say, step 1, and then I'll describe verbally in my own words, not looking in the book and seeing how they describe it or trying to remember what I said, but describe verbally what you did here. Step 2, describe verbally what was done here. Step 3, what was done here? Step 4, solution. And we're not going with the gnomes from South Park where half of our steps are just big question marks. One of my favorite South Park episodes. Now, one note here, we want these to be general descriptions. So in other words, I don't want to come back here and say step 1, subtract 1.1W from both sides. I want to try to think of this. I want to try to describe this in a way that when I have a different problem, I can apply that same step to a different problem, right? Subtract 1.1W from both sides is very specific to this particular problem. But can I say, okay, what was really the idea behind why we subtracted 1.1W from both sides?
To get the variable.
Sorry, don't answer, because we're going to be working through this. I want everybody to do this on their own. Yeah, sorry, that was more a rhetorical question. But so once we do that, once you've gone through and written out these steps in your own words very descriptively, then what I want you to do is to write down the new example below this one. This seems to follow the same pattern as that one we just did, right? It looks fairly similar. And to the right of this example, I would write down my same steps. Right, I would copy those same steps from the previous example that I developed. I'd write them here, and I would try to use those as a guide to solve this new problem. So I'm going to solve this new example with the help of these written steps. So I'm kind of going from a specific problem to a general idea, moving that general idea over to a new problem and trying to bring that down to the level of another specific problem. Now, it is possible that maybe the two problems aren't quite as similar as you thought. Maybe there is, one extra step here that needs to be done that wasn't done in the last one, or maybe the last one had an extra step that you don't need to do here. So there's a little bit of adaptation here. But the idea is to try to get us to think in more general terms about why we're doing the steps that we're doing back here. So I want to take about 5 to 7 minutes and let you all work on this. I want you to really spend, 3 or 4 minutes, spend a decent amount of time thinking about how you would describe each of these steps in general terms. So not just the basic, subtract 1.1W, but really what is the general idea that we're doing in this first, second, third step. And then copy those over and use that to solve this problem. And I think this is a good general study strategy. So that's why we're taking a little while to describe this and to go through it, because if you run up against a problem in the future where you're struggling a little bit, you can do the same thing with some of your class notes or the book, and that can be really helpful. So I'll give you about, let's say about 6 minutes, and we'll touch base after that. Okay, it's been about 4 minutes. So if you're still working, if you're going strong, keep going. But for just in case anybody is stuck, I'll kind of give you a little bit of a hint here, and then we'll talk through it in a couple more minutes. Okay, so we're the 6 minutes is up. So let's touch base. So the way that I might describe this, and your descriptions should be different than mine, or should be, slightly different than mine. They shouldn't be completely different, but it should still be the same idea. But step one, I see that I subtracted 1.1 W from both sides. And what was really the purpose of doing that was to get all the variable terms on one side. Now, I could write explicitly and simplify, or I could really think of that as being kind of an implicit statement. So either way, after each step, typically we're going to want to simplify. We're going to want to, combine like terms, reduce any fractions, anything like that. So you can either think of simplifying as being kind of implicit, or if that's something that you struggle with, if sometimes you forget to simplify and then things get really complicated, maybe it's better for you to write that out explicitly. Your instruction might be a little bit longer, but it's good to remind yourself of that. The next step, what did we do? Well, we had our variable terms on the left side all combined together. We wanted to get our constant terms on the other side, on the right side. So that was why we did the plus 50 here. And then we wanted to get our variable by itself. We did that by dividing by the coefficient of the variable. We got a solution, and again, if simplifying is something that you sometimes forget to do at the end, it might be a good idea to make a fifth step that's simplify. So we have kind of the solution, but it's kind of in a messy form. Maybe we want to simplify to get it into a nicer form. And we might want a fifth step to remind ourselves of that. When you get used to these instructions, you could write them a little more succinctly. So you might write, say, instructions 1 and 2 as something like isolate the variable term. And this is where math can get, a little bit esoteric, where a couple of words kind of, hides or acts as like an umbrella term for a whole bunch of meaning. And when we layer that a few times, if we're not really comfortable with both the ideas and the terms and the words that we're using, that can be really difficult. So steps 1 and 2, you might just see written in a textbook or something like that is just isolate the variable term. But, if you're comfortable with solving linear equations, maybe a week, 2 weeks from now, that might be enough for you. Say, okay, yeah, that's the first step. But as we're learning it, it might be better to break things out in a little more detail and a little bit more of a wordy way of saying it, but where there's less hidden behind things like variable term and different words and terms like that. Divide by the coefficient of the variable, we might, again, just say isolate the variable, or isolate the variable itself if we wanted to be very clear that we're not talking about the variable term. So we might just say, how do you solve an equation? We isolate the variable term, we isolate the variable, and we simplify. Right? Different people can have different numbers of steps. The same person can have different numbers of steps as they develop greater levels of comfort and familiarity with the problem. So then I would come over here and I would say, I wanted to add a 5th step, simplify. I would say, okay, what did I do here? I get the variable terms on the same side and simplify. We could write that explicitly, or it could be implicit. Get the constant terms on the opposite side of the variable terms. Divide by the coefficient of the variable. We've got our solution, and simplify. And now I'm going to use this as a guide to solve this specific problem. So thinking like this really helps us to recognize the patterns that are going on by abstracting away from the specific problem, getting a more general kind of structure to work under, and then applying that structure to a new problem. And again, I wouldn't say to do this for literally every problem you do, but I think this is a good learning tool or technique. If you're struggling with a topic, do 3 or 4 problems this way. And it's really the creation of this on your own that's really helpful. So don't, go and like look up somebody else's, answer to these steps. But creating it yourself is really what helps you sort out in your mind, okay, why did they do this step? And really understand it more deeply. Okay, but I want to get the variable terms on the same side. So maybe I'll subtract 1.7 W from both sides. I usually like to get the variable terms on the side that gives me a positive coefficient. I just have less negative numbers floating around that way, less negatives to drop off. But if you had decided to subtract the 2.9 W from both sides, that's a perfectly fine way to go about it as well. On the left side, 1.7 W minus 1.7 W is 0, minus 20. So if negative 20 equals 2.9 W minus 1.7 W is 1.2 W plus 40. I've got my variable terms on the same side and simplified, right? Yeah, so switching up the steps, I would say generally going in this order is probably it's probably good to stick with the same order, but then making those slight tweaks, like, why did I choose to subtract 1.7 W instead of 2.9 W? Subtracting the 2.9 W might have seemed to be a little more in line with what we did here. We kind of got the variable term on the left side. And if you had gone that route, it would not have been a problem at all. But you'd have been left with a negative coefficient of W, and that's just something that's an easy mistake to make. When you're dividing through by a negative number, just kind of forgetting about the negative or something is an easy mistake to make. So just, again, because I've seen these problems a lot, and I also recognize what mistakes I'm more likely to make. I try to avoid putting myself in situations where I know that I'm going to be error prone. So if I can avoid having negative numbers, uh, especially negative coefficients of variables, I usually try to avoid that because I know that's an area where I'll be error prone. But again, that's something that just takes experience, and it's also somewhat personal. Maybe you have uh, less of an issue with dropping negatives, but maybe you find fractions more challenging. So maybe you try to avoid situations where you have a lot of fractions. Okay, so I got my variable terms on the same side, in this case, the right-hand side, and simplified. I've got all of my variable terms collapsed into a single 1.2w. Get constant terms on the opposite side. Well, I need to get my constants all to the left side, so I do that by subtracting 40. 1.2w equals negative 60. Now, in a situation like this, if you have positive term equals negative term, somebody's got to have the negative. If I, had gone the opposite route, I'd have gotten something like negative 1.2w equals positive 60. And why do I care which one has the negative? Well, because now I have to divide by the coefficient of my variable. And personally, I just find it easier to divide by a positive number than a negative. I mean, mathematically, it's the same process. You're going to get the same answer. But I find that I'm a little more likely to, forget the negative or something like that, or make a silly mistake whenever we get to say inequalities, especially whenever I have that negative number attached, that negative sign attached. That's why I chose to do it this way. But again, you could do it the other way. You could have subtracted 2.9w from both sides. That would have been fine. So I divide by the coefficient of the variable, and I get w equals negative 60 over 1.2. I've got my solution now. This is the number that I can substitute in for the variable w all the way back up here. And the left side will equal the right side. And my last step, I would like to simplify. This is kind of a messy fraction. It has a decimal in the denominator. Let's see if we can simplify a bit. I know if I multiply by 10 over 10, in the numerator, that 60 multiplies by 10 to get 600. And in the denominator, 1.2 times 10, that just bumps that decimal one place to the right, giving me 12. And really, I guess I know that 600 is 60 times 10. And I know that 60 is 5 times 12, right? Like there are 12 hours going around the clock, and each one kind of represents 5 minutes. So 12 times 5 is 60. So 12 times 50 is going to be 600. So now I've got my solution in a nice, simple form. Okay, are there any questions on this? Any thoughts on this? Did anybody have a different set of instructions or a different way of describing things that they would like to share? Okay, I think, like I said, I think the two most important things here are number one, recognizing when you've come up against a topic that you're struggling with, recognizing that you're struggling with that topic. So, kind of having enough kind of self-awareness of the educational process to know, am I getting questions wrong because of, maybe a silly arithmetic mistake or something like that at the very end? Or do I really not understand the process? Do I really not understand, this part? Or is it this part that I'm struggling with? If it's this part I'm struggling with, that might just be a little bit of extra practice, some drilling. If it's this part I'm struggling with, that's more kind of, or likely more of kind of a conceptual misunderstanding or something that I need to practice more in that kind of conceptual or abstract area. And I think that's really where this helps. And again, the second thing that I really want to point out with this is I think that the most important part of this is constructing these descriptions yourself in the way that makes the most sense to you and that hits all of the points that you need hit. So maybe some of you would say simplify, and some of you would leave that as an implicit step. If you struggle with simplifying, if you find yourself forgetting to do that, make sure to write it explicitly. And then you kind of cement that understanding when you take that descriptive set of steps and you apply them to a new problem and you work through it yourself and you make sure that you can apply them. Okay, so I know that took a little bit of time to do, but I think that it's a super helpful, just general kind of learning strategy for math. A lot of people say, like, how do you study math, or how do you read math, or how do you kind of learn math kind of on your own? And there's a lot more self-directed learning in college than maybe in lower grades. And I think this is something that's super helpful. Again, if you're reading through the book, you read through an example, you do this, and then you apply this to another example. That can be really helpful. It's more of an active learning technique than just kind of letting your eyes skim over the symbols and you're kind of half asleep in the background. Okay, so let's look at now a general strategy for solving linear equations. So this is going to be basically writing out these directions here, but we'll write them a little more succinctly. So the first step that we want to do is actually always to kind of start by simplifying, by combining like terms, by using the distributive property where needed. So we want to get rid of parentheses, we want to distribute everything out, we want to simplify, combine like terms to get to something that looks like this. And again, like I said, with this method up here, you might have applied this method to this problem. And then maybe you come over here and you try to apply it to, let's say, a similar problem, but maybe we have this complication, right? Maybe this problem you say, oh, that looks similar to the previous one, but it has some parentheses here. So you might need to adapt your method. There might be an extra step here, like step 0, simplify or distribute, before we even start to get the variable terms on the same side. So you might realize as you're going through other problems or other examples that maybe you need to kind of slip a step in somewhere, or maybe we started with this problem and we had this step here, and then we see this problem and we say, oh, okay, I don't really need to do anything for that simplification step in this case. So sometimes you need an extra step, sometimes you get to skip a step. But here we're going to want to make sure that we simplify first. And again, we'll put it in standard form, and I like to have my coefficients of my variable positive when I can. So if a is bigger than or equal to c, if the coefficient on the left-hand side of x is bigger than the coefficient of x on the right-hand side, I'll first work to get my variables on one side, and I'll usually put them on the side with a bigger coefficient so that when I subtract big number minus small number, I end up with a positive number, and the constants on the other side. In other words, we might just call this whole step isolate the variable term, get the variable term by itself and the constant term on the other side. And then divide to get our solution. In other words, isolate the variable itself. Right. So our strategy could be as simple as 3 steps. Simplify and combine like terms, get to this standard form, isolate the variable term, isolate the variable. Or we could you know, as we're learning it initially, we could have a lot more steps. We could have 5 or 6 or 7 steps to make sure that we really hit every one of these little details and that we don't forget everything. So you could have more steps, fewer steps. You could combine steps into one, right? This step 2 here kind of combined into one step. The steps that we broke out a little more explicitly up here. And that's going to just depend on your comfort with the material. Now, something that we haven't focused on yet, because we've really been focusing on finding solutions, but a very important step, and something we really ought to do every time we solve a problem. And in class, we'll probably maybe do this about half or a third of the time, but you know, ideally you want to do this every time you solve a problem, is to check your solution. So we've really been focused on just kind of learning the process of solving linear equations, learning about different types of one-step and multi-step equations and so on. But let's go back to some of our previous examples. You might recognize these from the previous lecture, and we'll actually check our solutions. So if we remember, each of these solutions is a claim. It's a claim that I'm making. I'm saying, I started with this equation. I did some work, which I've, you know, not rewritten here, and I've gotten a solution, a equals -1. My claim is, if everywhere you see a in this original equation, you substitute -1, and then you simplify everything, the number you get on the left side, the number you get on the right side, they should be the same number. I've made a claim. I probably ought to verify that claim. Now, if I've done all of my work perfectly, that claim will be true. But I probably just want to double check. I probably want to verify that that's true. In the future, in more complicated, more challenging types of equations that aren't necessarily linear equations, I will get to the end. I'll have done a bunch of operations. I'll get to the end, but I have a risk of introducing what we call extraneous solutions. And in those cases, it's absolutely crucial to check your answer, because you could have gotten a suggested answer, a possible answer, that's actually not a solution. So this is a crucial step in the future. You really cannot eliminate this step and say that you have a solution in the future, even if you did all your work perfectly. In linear equations, if you did all your work perfectly, this will be the solution. But checking does two things. One, it gets us in the practice of checking our solutions, and two, it just gives us another way to check our work, right? It's much better if you're on an exam to check your work. Maybe you realize, oh wait, when I plug this in, I don't get you know, left side equaling right side. Something went wrong. Oh, I dropped a negative here, fix those couple lines, and now you get the question correct on the exam instead of incorrect. So it's usually a good trade-off, even when it's, you know, maybe not technically strictly necessary. But let's check our solution. So what does that mean? I want to take -1 and substitute it in for a. So I have 3 times -1 minus 1. Is that equal to 4 times -1? -3 minus 1 is -4. Is that equal to -4? And yes, it is. So I've checked my solution. I feel confident, and now I can move on. Quite often we get fractions as solutions. So we're going to need to be a little bit comfortable working with fractions. So is 3 times -6/7 minus 1, is that equal to 10 times -6/7 plus 5? Well, what can I do here? I mean, I suppose I could multiply both sides by 7 to check and get rid of the fractions. But that, you know, that feels a little wrong. I don't know. I think I just want to work with both sides as they are. I want to look at just this expression, simplify it, just this expression, and simplify it. I mean, if I think these two things are going to be the same if and only if they're the same when I multiply both sides by 7, but I would like to really keep my expressions separate. So this gives me negative 18 over 7. And then the 1 I'll make 7 over 7. Is that equal to negative 60 over 7 plus 5? Well, what is that in terms of sevens? 5 times 7 over 7, that's 35 over 7. I know a lot of times folks don't like dealing with fractions, but I think that it really is valuable to kind of get over that hesitancy and just get used to kind of working with fractions, get comfortable with them. It does take some time. It does take some practice. As an aside, the language app Duolingo actually has like one of their quote languages is math. You can actually go into their app and do math, and it's very gamified. It's very fun to do, and you can drill a bunch of math concepts, and they have a lot of fractions practice. So if you want to get extra practice on fractions, when you're falling asleep at night or wake up in the morning or something, and take a couple minutes away from scrolling social media, hop on Duolingo, do a session or two of practicing math, and it's kind of fun, kind of gamified. So if that's something that you're interested in, you can try that. But we now have everything with common denominators. Negative 18 minus 7 is negative 25 sevens. Is that equal to negative 60 plus 35 is negative 25 over 7? And it is. And even checking your work like this is a good way just to practice fractions. And I could do the same thing here. Is it true that 5 times 16 elevenths plus 7 equals 16 times 16 elevenths minus 9? So 5 times 16, well, what would that be? That's 30, and 5 times 1 is 5, plus 3 is 8. So that's 80 over 11, plus 7 times 11 over 11. 7 times 11 is 77 over 11. Is that equal to 16 times 16? This can be kind of a tough one, but we might notice that this is 2 to the 4th times 2 to the 4th. So if I take 16 and I double it 4 times, this can be maybe an easier way to do this mental math. Of course, you could do 16, multiply it out, no problem with that. But if I double this number 4 times, that's also my answer. So 16 doubles to 32, 64, 128, 256. And doubling a number is, usually not too difficult. So, and then 9 times 11 over 11 is 99 over 11. Now I have everything over common denominators. 70 plus 80 is 150, and then add 7 for the units. So 157 over 11. Is that equal to 256 minus 99? If I add 1 and then subtract 1, which would mean adding 1 here, I see this is 257 minus 100, which is 157. And I've verified that that solution is correct. So for some of these arithmetic things, I'll be going a little more quickly than we have been. We've been going pretty slowly through some of these fraction things and all that, but I'll be going a little more quickly. I'll be trying to show you some of these little mental math, tricks or shortcuts that I use, things like this. I noticed that 99 is very close to 100. So if I just add one here and then add one to 99, which subtracts that one away, that just let me do that calculation much more easily. Okay, so as an exercise, check these 3 solutions. I'll give you 4 minutes to complete these. And as I noted up here, be careful because there's at least one incorrect solution. So try to figure out which ones are correct, which ones are incorrect. We'll touch base in a few minutes. And I just realized the third one that I have here is actually, I mistakenly copied over the exact same problem that we just did. So I guess really focus on the first 2. Okay. So sorry that I grabbed the wrong problem for the third one. So I did just pop into WebAssign and change the due date on section 2.5, so that's already pushed back to next week. I do see that there are a couple questions. I think Sarah has a hand raised.
Oh, I was just gonna offer to go through the problem.
Okay, yeah. Yeah, do you want to work through the first one?
Yeah, I know that the first one's correct, but I also know that the second one is, even though you did like copy them and you're like one of them's wrong, but like the second one is, which I found really interesting, specifically about the second one. Sorry, I'm like off track, but like specifically what I found interesting about the second one is how like to the point wrong it was, because you do 15x minus, like the way that I was taught to do this was that you would like take, you would try to like, you separate them on both sides, but you'd like minus 15x from 16x, which would get
Hmm.
you 1x, and 1 times whatever number is always that number.
Yep.
So 7, so 1 times 7 is 7, so it can literally not equal 8. There's no way, and no physical way that it can equal 8.
Yeah, exactly.
Which
So
I
I
guess an
mean,
easier way would just be to like plug it in and then do it that way, but at the same time I feel like simplifying it is also a much easier way to do it, in my opinion, at least. I don't know. I'm
yeah,
not a math
exactly. Yeah.
person, so maybe that's just, it's
No,
easier for me at least.
no, that's a good point. Is for this one, we could see that it's not a solution by just subtracting 15x from both sides. Like you said, we get x equals 7. So that's something like solving it from first principles. Um, but I mean, you would be surprised the mistakes that I see. People make mistakes all the time. Sometimes people make mistakes copying. Um, so they might, get like, 1x equals 17 or something like that. They might just copy it wrong, or they might get like 16x minus 5x. They might just forget to,
Yeah.
when they copy the 15 over, it might come over as a 5. So people make transcription errors, people make
Mhm.
sign errors. So there are all kinds of errors that can be made.
That's just
Um,
how I was taught, so it's like the easiest way for me at
so,
least.
yeah, so the problem, or the really the thing that we want to do here though is, so what you're saying is if you just solve the problem, then you don't get x equals 8. But keep in mind the context. The context is that, we were assigned this problem. We did a whole bunch of steps. So we did all the steps that you're saying, and we came up with a solution. So if we just were to say, okay, go back to the problem and repeat those steps from first principles, we're likely to make maybe a similar error, or at the very least, it's going to, you know, probably take a little bit longer for most problems. Now, this one is a pretty simple problem. But if we just go through the same method again, it's not really kind of an independent check. But what's more of an independent check is to take the solution. We're making a claim that if I replace all of these x's by 8s, these two sides of the equation will be the same. That's the claim I'm making here. I want to, if I check this claim directly, that's kind of an orthogonal method. It's a method that's different from the method that I use to generate this answer. So if I plug in 15 times 8 plus 7, and I ask, is that equal to 16 times 8? Well, I can use that same doubling trick here. This is 2 cubes, so 16 doubles to 32, 64, 128. Is that equal to 15 times 8 plus 7? 15 times 8 is, well, 8 times 10 is 80. 8 times 5 is 40, so that's 120. 127. And I see that that's not the case. So I made a mistake somewhere. This is actually not a valid solution. And then I would go back and check my work. Um, you know, when we're checking work, we could go back and kind of check line by line and kind of check our work that way. But the thing is, though, that if we made a mistake at one line while we were doing the work, it's really hard for us to kind of go back and check completely independently. We're likely to make that mistake again or to kind of gloss over it. But by plugging back in, this is kind of a completely different method than the method that we use to generate the solution, which was, isolate the variable term, isolate the variable, simplify. Um, this is really a very different method. So that's really the benefit of this solution step. The second benefit, again, is by going through this process now, there will be examples later on where this kind of, step-by-step solution method will introduce what we call extraneous solutions. It'll introduce things that we're saying might be solutions, but actually aren't. And in that case, going back through the same steps would introduce those same extraneous solutions. So in that case, it actually is a very important mathematical step to plug back in and verify that. Typically, this comes up with things like equations with square roots, things like that. But for those two reasons, I think it's good to go through this process of plugging back in and simplifying. And then for a longer equation, say like this one, maybe it might actually be quicker to do the plugging in step than to repeat all of those steps. So for a simpler equation, maybe it's quicker to just kind of go back through the same steps. But again, you might be prone to make the same error, and it's not an independent method of checking, and it doesn't generalize to those ideas in the future. For the first one, this is correct. If we plug in a equals 4, we get 16 minus 7 on the left, and that is a solution. Okay, so, and then my mistake, we already did the third one. We did that back here. Okay, so moving on to section 2.4, working with this general strategy that we developed up here. We want to simplify to get a standard form, number times x plus number on each side. We separate our variable and constant terms. We isolate the variable term. We divide through by the coefficient of the variable to get the solution. We isolate the variable, and then we check our solution. So those are the steps we're going to go through for our strategy. Now, this problem has kind of that, maybe 0th step, right? Or sorry, that first step. It's the first step up here. It was what we said was kind of the 0th step when we were writing things out more explicitly. We need to do some work to get this into number times variable plus number equals number times variable plus number. The right-hand side is already in that kind of simple form, but the left-hand side is not. I have to distribute this 3/4 into these two terms, and then I want to combine like terms. So I've got a little bit of work to do in the beginning to put this into a nice form that I can then use my general strategy on. And again, why do I care about putting it into a nice form? Because when I get it in that nice form, number times x plus number on both sides, that's a pattern that I recognize. That's a pattern I'm comfortable with. I've reduced this problem to a previously solved problem. That's another big idea in math, is I don't really recognize this pattern as I see it directly here with, the coefficient times the parentheses and all of that. But if I do some simplification, I can work towards something that looks familiar. And then once I recognize that thing that looks familiar, I can just move forward with my general strategy. And I just realized in chat, there was a question. So Amani said, I have 2 questions, not about these problems. If it's like a personal question about your particular homework, I have office hours afterwards, but if you have questions about class material.
Yes, no, it was,
yeah.
Sorry, it was 2 of the questions that you went over previously, but I can.
Okay, yeah.
Okay, yeah. So it was 2 of the tricks that you were talking about. So for the decimal trick, is that something that we can always do with the decimals?
Was that over?
No, it wasn't this question, but it was sorry, to bring you all the way back.
No, that's fine. Was it this one where we multiplied by the?
Yes.
Okay, yeah. So if you have a decimal that's written like this, then the answer is yes.
Okay.
Even if this was like 1.273, I just need to bump this decimal 3 places to the right. So I need to multiply by 1,000 on the top and bottom.
Heard. Okay.
If we have something like negative 60 over pi or something like that, right? Where
Mhm.
like this is like a decimal, but it kind of goes on forever. Or if we had like negative 60 over like 5.3 repeating, that would be kind of a terrible way to write that. But something like this, that wouldn't work for, because if I bump this decimal over 1, I just have 53.3 repeating. I didn't really get anywhere. Or if I have pi times 10, like I have 31.4 and so on forever. So it works for decimals that terminate. And then kind of practically speaking, it works pretty well for decimals that don't have a whole lot of decimal places after the decimal point.
Okay.
So it's fairly easy to multiply by, say, 10 over 10, or maybe even 100 over 100, and then simplify. If we're multiplying by like 10,000 over 10,000, the numbers might just get a little bit out of control. And then we might want to look and see if there's a different approach. Maybe we can convert to a fraction, and maybe that would be a better approach.
Okay, thank you. And
Yeah,
then
yeah.
sorry, my last question was, you did like oh my gosh, sorry, it was the third example. 5x plus 7. Yes. So
Mhm.
when you did the 2 to the power of 4, I do understand how you got 2 to the power of 4, but I'm just a little confused how you got to 256.
Oh, sure, yeah. So
Thank you.
we want to multiply 16 times 16, but that's 16 times 2 to the 4th.
Mhm.
Well, what I can do is I can, or let me even write it this way, like that. But I have this associative property that says I don't have to multiply like the 2's together first. I can kind of change the order of the parentheses. Oops. So I can put this 2 with that 16, just that first 2. So I can
Oh, okay.
double the 16 to be 32, and then I
Mhm.
have 3 powers of 2 left over.
Okay.
Then I can do it again and get 64 times 2 times 2, and again for 128 times 2, and then 256. Yeah. And I mean, I've done math for a long time, so I tend to kind of know the powers of 2 just because I'm a nerd like that. So but even, just doubling 64, we can see that, doubling the tens place gives us 120, doubling the units place gives us 8. So like, doubling numbers tends to be, pretty easy to do, or tripling numbers tends to not be too bad. If we get it to like, 5 times or 7 times or something, it gets pretty messy. So if this was like, 7 to the 4th or something, that would be a big mess. But because I recognized that this was 2 to a power, that just meant I could double 4 times,
Mhm.
essentially just pulling off one of these factors 4 times and then sticking it onto the original number. Yeah, but good question.
Thank you so much for going up.
Yeah, absolutely. Sorry that I missed that in chat until a little bit later.
Oh, no, you're fine. I just didn't want to interrupt.
No, you're good. Okay, so in 2-4, solve this problem using our strategy. We need to first get to that standard form. We need to distribute first. So 3/4 times 4 is going to be 3 times m minus 3/4 times 8. So I know that the 3/4 times, say, 8 over 1, that factor of 4 will cancel and give me 6. I see this gives me 3m plus 1 equals 4 minus 2m. And now I'm kind of in this standard form. I see that the 3m is bigger than the minus 2m. So I get my variable term on the same side by adding 2m to both sides. That is going to make my coefficient of my variable positive. I've got my variable term on one side. Then I want to isolate my variable term. I want to divide. And then I would go ahead and check. I'll leave checking this solution as an exercise because we're running a little short on time. But I would plug m equals 3/5 back in and carefully go through all the fraction work, make sure that everything balances out. So we can see that section 2.4, this is really, this same idea that we were developing up here in this example from 2.3. And really in that Cornell method, we were coming up with our own way of kind of making a general strategy to approach these kinds of problems. So not a huge leap in section 2.4, at least not in the first half or so of it. Now, something different that comes up in 2.4, something like this. Let's start to work through this problem. Well, first we have some simplification we need to do. This doesn't look like number times x plus number on both sides. I don't really recognize this pattern. Is there something I can do to work my way towards that pattern? I can start by distributing. I have 10x minus 5 plus 7 equals 2x plus 6 plus 8x. I've gotten rid of all my parentheses. I've multiplied out everything I can. Now I want to focus on the addition subtraction side of things. Can I combine like terms? I have lots of like terms I can combine. 10x plus 2 equals 10x plus 6. Now I'd like to get my variable terms on one side. Maybe I'll subtract 10x off of this side. And on the right side, I get 6. But on the left side, unfortunately, or maybe not unfortunately, I suppose we maybe aren't emotionally tied to this thing having a solution. But 10x minus 10x on the left side, they also happen to go away. So what the heck do I do here? All of my x's went away, right? Did I do something wrong? Well, no, I mean, my distributive properties, I did those right. My arithmetic was right there. I simplified, right? I combined all the like terms, right? I did all legitimate properties. I didn't make an arithmetic mistake. It just is fundamental to this problem that the x's all kind of go away whenever we try to get them on the same side. So how do we handle a situation like this where we work our way down not to something like x equals 3, but to something like this here, where I just have number equals number and my variables all went away? We're going to skip this one, mainly for time. This one would not have the same problem as up here, but let's put that in as an extra practice problem for section 4 if we needed it. So it turns out that there are 3 types of equations. The only type of equation that we've seen up to this most recent one where we had this kind of problem happen was a conditional equation. What do we mean by conditional? We mean that there's a condition for this statement to be true. Remember, this equal sign says that this left-hand side and this right-hand side are the same. That's a statement of fact. It's a claim. And if I pick some values of m, like say m equals 0, I would get a left-hand side and a right-hand side that are not the same. So I have a condition that up here, this equation is true. The left-hand side and the right-hand side are the same under the condition that I only substitute in 3/5 for my variable. If I substitute in 3/5 for my variable m, in that situation, the equation balances and we're happy. If I substitute any other number in for m equals 0, m equals 100, m equals -10, I get a claim that's not true. I get an equation where the two sides are not the same. So we call that a conditional equation. We get down to something like, x equals 3. We have two other types of equations, though. Two other types of situations that can come up that we've been kind of intentionally avoiding up until that last problem. These are the types of equations where when we start working through our steps to solve them, kind of all the variables go away and we're like, what happened? What do I do now? So let's take a look at 3 equations here. And these are going to be one example of each conditional identity and contradiction. X plus 1 equals 4. If I subtract 1 off of both sides, we get x equals 3. Well, this is a conditional equation. This statement is true if and only if the number that I put in for the variable is 3. If I try to substitute in x equals 0, 0 plus 1 does not equal 4. That's not a true statement. So I have a condition in order to make my equation true. X has to only be 3. That's the only way that my two sides of my equation balance. If I look at this next example, let me multiply out the right-hand side. I have one thing, 2x plus 2, that I'm claiming is equal to another thing, 2x plus 2. But these are exactly the same thing. I mean, exactly the same thing. If I plug in x equals 0, what do I get? 2 equals 2. If I plug in x equals 10, what do I get? 22 equals 22. If I plug in x equals -5, what do I get? -8 equals -8. This equation is true for any x. I could plug in any value of x I want. I could put in a positive number for x, a negative number for x, a fraction, x equals 0. Because these two sides, algebraically speaking, are the same, it's just saying this expression is equal to itself. Of course, that's true. We call that an identity. When we have a statement that is always true, regardless of the value of the variable we put in, we call it an identity. Up here, this is true. This equation is true only if this condition is met. So we call it a conditional equation. And then down here, what might I do here? Well, I can imagine plugging in different values of x, say x equals 0. Then I'd be claiming that 1 equals 4. That's clearly not true. If I plug in x equals 5, is it true that 6 equals 9? No, that's clearly not true. Whatever number I plug into the left and plug into the right, these are always going to be different numbers, regardless of what I put in for x. So I take x on the left-hand side and I increment up by 1, wherever I am on the number line. Doesn't matter where I am. The left-hand side says go up by 1. And the right-hand side, oh, I missed one. The right-hand side says go up by 4. These are never going to be the same number. If I start somewhere in the number line and I move to the right 1, and if I start at that same place and move to the right 4, those are never going to be the same number. No matter where I start, I'm always going to be 3 apart. If I started to go through my solution method, isolate the variable term, I would get 1 equals 4. This is never true. no matter what value of x I put in, this is never going to be true. I call this a contradiction. This statement here that x plus 1 is the same as x plus 4 can never be true, no matter what value of x I use. It's a contradiction. So practically, what does this look like? When I get the same thing on both sides, if I were then to go and subtract 2x, I would get 2 equals 2, which is a true statement all the time. No matter what value of x I substitute in, I just have 2 equals 2. It doesn't care what x I put in, this is always true. Versus down here, where my x's all went away, no matter what x I plug in, I always get the claim 1 equals 4, which is never true. There's no x I can plug in to get a correct solution. So let's look at a couple examples, and I'll go through the algebra here a little quickly. I recommend going back through these examples after class, working back through them. But I really want to just get to the end and show you what this solution, what these different types of solutions will look like, what these different types of classifications look like. We'll distribute the 2. We'll combine like terms. And 46 minus 14 is plus 32. And I can see here that I have exactly the same thing on both sides. I can already see that. But if I want to step further and I started following my strategy, I would see I get 32 equals 32. My variables all went away. That doesn't necessarily mean I did something wrong because my variables went away. But what I'm saying is that whatever value of x I plug in up here, that's always going to give me a true statement, because this, we no longer have a condition on x. Up here, this equation, if you wanted to call it that, x equals 3, is only true if I substitute in 3 for the variable. That means this equation is only true if I substitute in 3 for the variable. This equation is true no matter what value I substitute in for x. Therefore, this equation is true no matter what value I substitute in for x. This is an identity. My solution is all real numbers. Any number that I substitute in for x, the left side will equal the right side. And now in the last couple minutes, I just want to go through a similar looking problem, but we'll see it has a slight difference. And again, I'm going quickly through this because I want to make sure to get through this topic before the end of class. Be careful with the negative. So this is plus 70. 11x minus 54 equals 32 minus 21 is 11x plus 110. Now I go through and I subtract off 11x from both sides. I get negative 54 equals 110. Whatever value I choose for x, negative 54 is never equal to 110. This is never true. True. Not true for any x. Which means regardless of what value of x I substitute in the initial equation, that initial equation will never be true for any x. There are no solutions. This is a contradiction. So if all of my variables go away, that means I'm in the situation where I either have an identity where any number can be substituted in for the variable and yield a correct solution, or I have a contradiction where no number can be substituted in for the variable and yield a correct solution. And the way that I tell the difference is whether, when all the variables go away, the resulting equation is true. 32 equals 32 is a true statement. That means it's an identity. Solution is all real numbers. Or when all the variables go away, if I get a result that is false, negative 54 is not equal to 110, then we have no solutions, we have a contradiction. Okay, so this finishes up 2.4. Let me stop the recording here.